So we're heading into our plenary discussion, challenges and opportunities in geosciences, and I'm very happy that I may welcome all of today's speakers back. Guy de Arne, Eric Larsen, Xiaopeng Shen, Begüm Demir, and of course Niklas Klein and Thomas Zerweg. As I said yesterday already, it is a plenary discussion, so all of you are invited to participate. We had some great impulses yesterday also from the audience, so I'm looking forward to this discussion. And I would like to start with I wouldn't call it a, provocative question. If you know all the physics as a scientist, do you even need AI? Would you want to? Yes, of course.
I think that's a great question. I think we still need AI because AI adds this new layer of knowledge discovery. In a sense, we think about the fundamental aspect of deep learning is that it can go from one end to another without the supervision of an expert. That make us worry about it. But the other aspect of this is it can discover knowledge by itself. So I think that provides an opportunity to use it as a knowledge exploration tool. Especially in our modeling department, we have so many assumptions, so many things that we just assume for truth. So there's a tremendous opportunity of using machine learning to advance beyond our present models and correct our assumptions and identify new things that we didn't even know.
Also, for example, physical models and machine learning models, they can be very complementary to each other. That can, if we find efficient ways of integrating them, using them together, the performance of a given application could be significantly improved. So this is also called nowadays like physics-driven machine learning. So it's especially for hydrology, for example, I think it is very relevant. So how to improve the performance of physical models by using machine learning models. And on the other side, it's also very important nowadays, this explainable AI. For example, for hydrology, we have seen that LSTMs are used, and LSTMs are very popular for hydrological applications. But there are great works going on with, for understanding the memory cells of LSTM is how they are correlated with hydrological states, for example. So I think, yes, we still need AI for learning more information.
Thank you. Eric?
Yes, and for these composite problems, like I were pointing to in my presentation, where you want to end up with the basis to make some decision to invest or any type of decision, the workflow that leads up to the decision is often a relay of different disciplines. So you need to have somebody who knows the physics of data type A, another person knows the physics of data type B and C and so on. And we have seen in my line of work that you lose information when you pass it on in this relay. And so there is an advantage of the machine learning models that just make it flow smoothly all the way.
Yes.
I think understanding the physics perfectly of, in my field, ore deposit models is almost impossible. The level of data is scattered and imperfect. So I think the added value of machine learning is as you stated elegantly, is the error bars, is understanding the uncertainty. I think we can learn a lot more about what we're looking for and what's the uncertainty that we're going to be able to model correctly the reality of nature.
You said before you could talk an hour about the problems with data.
Yeah. So this plenary is now just for me for the next hour. In resource estimation for mining, and it's much beyond gold, but any type of ore deposits, it's a mix of perfectly well-distributed geophysics or hyperspectral maps, which give you an idea of what's going on the surface. But then to bring it into the third dimension, you need to either cheat that 2D data into the third dimension with inversions, or you have drill data, which is nice to have as a punctual version of the truth, but then you need to interpolate between those drill holes or extrapolate, and that there's a lot of danger involved with any method of interpolation, extrapolation, and those are the main issues you need to deal with. Then you sort of need to pick a size, a pixel size. So this comes back a little bit to the question about the pixel size for the insurance. In that, you know, if the before and the after doesn't have the same level of information, how do you then translate and account for the error just based on that calibration? So there's different levels of raw data issues, scaling, quality, reliability, and just general distributions is things you need to deal with and think about as an expert.
So I think we all stand on different parts of the spectrum. I'm kind of right in the middle. I think I'm going to quote my colleague Grenier, and I don't think he mind that I'm quoting him. He's a much more fierce argument. So there's been a vote on 23 unanswered questions in hydrology, and one of the questions that one of the audience raised is, does machine learning have a role in hydrology? And that question wasn't selected as one of the 23 questions. But Gray's point, which I agree to a certain extent, was that we should not be asking, is there a role in machine learning in hydrology? But maybe we should be asking, is there a role for hydrologists in machine learning? Because in the future, there's a bunch of startups that's going to come out and make predictions that beats existing models. And the question is, what does hydrology offer? And the society actually doesn't really care about our ego. It doesn't care about our emotions. It doesn't even care about our curiosity. It cares about what kind of services it can provide and what accuracy you provide them at. So I think that's a different way of looking at this question. I'm somewhat on to the left of Gray, I would say, at that.
And on this physics versus machine learning topic, it's also worth mentioning that when we prepare slides to give a talk, we tend to select something that looks nice. And there's a jungle of examples that don't. And it's important to highlight that some of those, we say the mistakes that the neural network makes can be like totally ridiculous. It's nonsensical, and no human would ever make this kind of mistake. So, but this has been addressed, this need to kind of integrate physics and machine learning to kind of stay within the legal distribution of some property.
But you also said that humans make mistakes. So what do you think is the bigger problem? The humans making the mistakes, or the machines making the mistakes?
I think for now and in the foreseeable future, it's a good idea that humans are driving machine learning, and you have an eye on the output and just don't trust it blindly.
So, sorry, do you?
I do also think that it's not, the question is not necessarily whether a machine learning system can completely replace a human. The question right now and in the next couple of years should rather be whether a AI system or a machine learning system plus the human will result in better results, will yield better results.
So we teach machines and predict from the data, right? Mm-hmm. So if we can teach the machines to learn also how to handle the complex cases, for example, learning how to model the data if the labels are incomplete, noisy, that I was also mentioning in my talk, then we can predict better results from the data. So we are the one who should teach the machines to predict better results. Mm-hmm.
Yes, and there's a huge scope for that in the geosciences, because the examples we see in various talks, somebody has trained a model on some data, but that data does typically not cover the entire distribution of this problem. So when this trained model is exposed to some data that is different from what it trained on, that's when it falls apart. But of course we can work to build more complete training sets, and that we're just in the beginning of that journey, especially in the subsurface field.
Guy, you mentioned that you looked into machine learning and looked at all the videos and educated yourself. How far do you think do geologists have to go? Do they have to basically turn into data analysts or computer scientists, or are computer scientists going to take away the jobs of geologists?
No, I think all universities worldwide should have a course. As now, basically, you need to take a basic statistics course. I think there should be a machine learning course imposed as a graduation requirement, because it should be part of the toolkit. It will be a part of the toolkit. Anybody graduating now or in the last 5 years that did not learn machine learning in university is handicapped. However, it's such an interesting time in history where such a powerful tool is developed and is completely available for anyone to pick up. I don't know in history if there's ever been such a technological a tool, something so powerful that's not developed by the American military and kept in-house for 20 years and then slowly leaked out, whereas now it's basically, if any scientist or anybody is curious, they can quickly get up to speed. The data is largely available if you want to play. The software is completely available, and there's lots of free online courses available for people to just pick up and go. So it's not so much a matter of accessibility, it's just a matter of motivation, and you need to have a little bit of capacity to learn coding and understanding data to do it.
Within Munich Re, they currently have a program where they try to get a lot of the underwriters, so that are the guys who actually do the business, to a so-called black belt data analytics type of thing. And I'm not so sure if this money is really well spent, to be honest, because I think if to understand all these methods, you really have to work with them in your daily business, otherwise you simply will forget them. I think what is important is that everyone has an idea what it is about and how to use it possibly for his own purpose. But then you need the specialist to actually do it, I think, because otherwise you would not be able to do both your normal job, so to say, and to do a fancy data science, data analytics job. So that's the reason why we are two of us.
However, I think even if you're in a position, maybe you're a leader of a technical team or some other role where you're not going to do the technical work yourself, it is very much within reach to gain some understanding of what is this. So you're not going to be the person who does any physics predictions either, but we took a technical education once upon a time, and so we have some basis of an understanding. So we get away from this idea that there's some kind of magic happening underneath the hood. It's linear algebra, probability, matrix multiplication. It's things that lots of people can take in fairly easily. And there's tons of free material online to self-educate.
Sharing some of my personal experience with respect to this topic, even though I'm applying these methods on my day-to-day work, it's kind of difficult to keep up in a field that is literally reinventing itself. Every couple of months there are so many publications produced by everyone out there, and that's really difficult when you're out of academia to keep on track and use the latest cutting-edge methods. That's difficult, and that's probably requires a cultural change also in the companies. If they decide they have the will to employ these methods, they must be aware that people using the methods require a decent amount of time to familiarize themselves with the latest technologies every couple of months.
I would like to ask what your experiences are in the motivation. Do you feel that or how do you motivate geologists to learn about machine learning? Do you feel there's a big acceptance? Because, as you said, the younger generations, they'll probably have it implemented anyway in their education, and also the other way around. What about computer scientists? Do you have to motivate them to be interested in geology? So, both sides of the motivation.
Okay, so I will start by giving an example. At TU Berlin, for example, we offer courses to non-computer science students on data science. So we teach data science, how to handle data, what is data processing, what are the applications that that are better to be learned, for example, and there is a huge interest. So this is open to all the students in Berlin universities, and I heard that I'm not one of the professors teaching in this class, but I heard that there are a kind of 1,000 students coming, listening, and very much interested. So I also heard that in Germany there are several master programs of several different universities now for non-computer science students to learn data science. So there's a huge steps already taken and also going on to teach the basics of data science and how to program, and I find that very relevant. And of course, I enjoy very much, and I like it really very much, to collaborate with domain experts. For example, we are developing machine learning algorithms, but we don't have really the domain information. If we understand this, we can really create amazing systems, but we need to understand, we need to also learn from them. It is not only that they need to learn from us, we need to learn from each other. That's why collaboration is very important, and for the education side, there are works going on, and there are courses now, especially for the non-computer science students.
But those are also the younger generations?
Yeah. Younger generation, I talk for bachelor and master, but do you mean high school or?
No, what I mean is...
Because also in high school something is going on in this direction.
No, I mean the other side. What about the older generations? How can one motivate them, or are they open to education?
Well, I would say it depends on if you mean education or acceptance of the methods, because when you look at business, at the end it doesn't matter. So what is the idea, for instance, of an insurance company to sell insurances? So at the end, it's not about maps, about geospatial analytics, about machine learning. It's about selling insurances. And if you can improve that, if you can improve the predictions, if you can speed up the processes, then you're good. Then the method is worth it, and then it is accepted. So you always have to prove the value of a certain method, and then it will be accepted.
Okay.
So that's completely agree with that. I think with a market-driven industry, it's much easier to accept machine learning because the results speak for themselves. However, for industries that somewhat more or less sponsored by the government, for example, hydrologic predictions, the government is paying for some of the work. That takes a bit more time, because that has to penetrate from the up down. But now I'm seeing a lot of startup companies that's trying to fill the gaps. That should serve as a motivation for hydrologists sitting comfortably, because the market's opening up, but the startups are taking the piece of the pie. So you should not let that happen. The other part about motivating computer scientists, I think there's one stream of computer scientists that holds as holy grail that you should not be using any domain knowledge when you're training the model. There's almost like a cult that says, we should want to train models that's completely dependent on data and no knowledge is involved. However, I think that VPing has promoted the idea of physics-guided machine learning, and I think that's the right approach. I have made this. When I was educated, I was educated by this computer scientist, so I was in that cult. But then I have circled back, and I really feel like the need to combine the physics with the machine learning, and I think that those type of models would be more powerful than the only kind of data-driven one.
Coming back to the generational divide, I think there's definitely a trust issue. Like the management level positions don't, especially on the mining side, where it's oversimplistically thought of as we break rock, we move rock, we crunch it, and then we get the metals out. How can data increase my profitability of that rock, right? And I mean, convincing upper level management that there's benefits to be made is very hard, because those gains are going to be small, incremental. If you remember the EKG chart of what the processing recovery is on the charts that I showed, it's very small losses that you can eliminate just by stabilizing. If you understand what your process is doing and the rocks that you're delivering to the process plant, you can make decisions that make you more money, but it's hard to wrap that around a very sexy proposal for the upper management. And so what tends to happen in the mining, all the press releases are basically saying, you know, we're doing this fancy new AI thing, but it's a thinly veiled attempt at increasing their PR, unfortunately, currently. So there are companies that are more forward-thinking, that have built teams, multidisciplinary teams, which I think is important, combining domain experts that understand the language of machine learning and computer scientists that are slowly getting into understanding what the domains are like. And so those companies are going to benefit in their productivity and the profitability, but it's going to be hard to compare the before and after, because it's all going to be small incremental gains that are just driving the bottom line.
Do you think it's a communication problem? Or what would you say is the...
Yeah, definitely a communication problem. The trust issue is a lack of understanding. But it comes down to trust and explaining what the problem is.
Yeah. In oil and gas, where I come from, I see that there's a push from the management and the board and even the owners to do something digital. So they often don't have a very specific idea of what to do, but digitalization is happening. We've seen it in other sectors. If you don't follow it, you're going to fall behind. So it's pushed down the organization, and at the bottom, with the young people, there's always a lot of enthusiasts coding themselves, building models, and we see this resistance most with the kind of senior scientists who are very ingrained in the physics-based methods. And I think we work with them all the time and familiarize them with what is actually going on under the hood, like take away the magic of it. And it's perfectly understandable, the basics of machine learning, for anybody with a science degree. Of course, it's hard to keep up with all the new developments, but you don't have to in order to get a feeling for what this is at the core.
So you feel that if you open up, that it's just a problem of communication, and if you open up and communicate and explain, that they're also more open to the new technologies?
Yes, open and honest with the results, and focus on how you can measure performance honestly. And some of the lack of uptake of these tools is related to not only the understanding of the maths behind it, but the fact that you might need to write some code. So that might be a blocker for some people. But there's a lot of software coming up where you can exploit these tools without writing the code. So it's also available if you don't want to take that route and educate into coding when you're a senior. You might not want to do that. But I would encourage everybody to have a go, though.
Okay. And you mentioned trust. My question would be if how do you avoid or try to minimize overestimations and pitfalls? Because of course, the more of them you have, the less trust you can build.
Sorry, resource overestimation, the graph he showed in petroleum is, I find it hilariously good compared to the track record in the mining industry, where there's been a rash of resource overestimations, but those, at the very basic level are due to human issues, overconfidence and people driving projects forward regardless. So I think on the data front, those are minor issues compared to the human decisions and the base parameters used to make those decisions.
So would you say if you rely on the data instead of human decisions, then you can avoid overestimations and build trust that way?
I would be concerned, and people ask me, oh, shouldn't we be using machine learning for resource estimation? And for me, there's so many foundational issues with the way we're doing. It's just adding a layer of digital magic doesn't increase the reliability because of the data and the way it's treated ahead of the machine learning. But
so just briefly, I think the solution to this problem, the decision maker is faced with the basis for the decision, so machine learning is part of it, but the human experts that were part of making the decision basis previously should still be part of it, and if they can learn to drive the machine learning processes and the data analytics processes, we will be in a better place. And this is possible now for general scientists to adopt these tools.
Another aspect of trust is if you want to explain what your model is doing, and this is often the most difficult question. How do you explain what the machine learning model has done? And this relates to the explainable AI. But I read through a lot of the explainable AI approaches. I realized it's really not a problem that can be tackled in a general way, because each domain, if you want to explain something, you need the terminology from that domain. If you want to explain how did you produce a stream flow, you need to other variables. For example, the soil moisture here, the groundwater here, the vegetation canopy storage here. So if you don't have those variables, how do you even build a linguistic system to explain your results? So I think the explainable AI in the end is going to be a domain-by-domain exercise that the science can come in and help translate the machine learning model into understandable variables in the middle that can explain the whole process.
So I fully agree with that. Explainable AI for geosciences and remote sensing, I think, should be driven by the physics-based information. Usually nowadays, most of the researchers, they just take from the shelf a deep learning model, let's say machine learning model, and apply it for the problem that they have in their hands. But this is not how it should be. Right? We need to question what we really need to learn, which model is much more proper for it, and what we are learning. So the answers are hidden in explainable AI. Computer scientists can approach to explainable AI from the math point of view, from the mathematical point of view, but there they also need physics-based information to explain if the results, if the predictions are in line with the expectations of the algorithm. So the domain information is really very important.
You mentioned open data spaces, that you said you feel that is really, really important. Do you think that is generally something in geosciences that they need to learn about this from this philosophy and be more open for open sharing of the data?
Yeah, so I think that remote sensing researchers, until a few years ago, they were not really very open to share the data set codes and so on. There are different reasons behind, of course. Maybe you need to be very much sure on your code, right, before publishing. Maybe that's why they were not very much sure to publish it and so on. But nowadays, it's almost impossible to reproduce everything if the codes are not shared. So we are, in my group now, sharing all the codes that we are producing. For every method, we are sharing the codes, and we think that that is very important, because afterwards, somebody can also complain if you don't share the code, okay, with your approach, we don't obtain the similar performance, and so on. This is also to address this problem. But about data, also, I mean, in the recent years, as we also listened yesterday and today's talks, now we are interested in publishing the data sets, but it is just the beginning. I think the mind of remote sensing researchers is recently changing to share the data, but it was not common at all in the past.
2 days ago, there was some news from the EU about the ambitions of sharing data in Europe. So very good messages from there. Of course, it's hard. Data collected by companies is a competitive edge for companies, and they will push against releasing it to the open. But data acquired with taxpayer money, it just makes sense that it finds its way back to the community to be used. And these machine learning models, they typically are narrow because they were trained on some little sliver of data from some area. If you apply them somewhere else, they will fail. And there's a funny example there from a talk I saw a few months ago in Norway. A guy was training a model on multiband satellite imagery to predict tree height. But the training data was from East Africa, and it made a prediction for the entire continent. So obviously all of Sahara was green, because there is no desert in the training area. So it's just a funny example of how narrow the training sets can be and the effects that it can have. So we all know, we all will spot this mistake. So have a human in the loop to spot ridiculous mistakes like this, but sometimes it's hard to, even for the humans to spot it. So there are some pitfalls.
I mean, this is about the generalization capability, right? So that is a big problem that we are also facing. So if you have a machine learning model that perfectly works for a given geographical area, it may not work that perfectly in another geographical disjoint area. Okay, there the direct use of the same machine learning model, I think it is not the optimum solution. The solution is through domain adaptation. So how we can adapt the machine learning models that are defined for a given geographical area to another spatially disjoint areas. So the network, the model should not be directly used, but some domain adaptation methods should be used there. So we need to increase the model's generalization capability through domain adaptation. Yeah, this is a big research problem also in machine learning.
So we have a question from the audience.
Yeah, maybe building on what you said and also looking forward, big data, machine learning, I am worried, not because maybe job security or expectations of careers, but more about sustainability of big data, machine learning in geosciences. And let me explain why. 2 examples. We have seen in the past hypes of new technology coming in and then waning away. In big data and machine learning, these are terms in Gartner, which had already their due date, if you like. They're already out of fashion and going through this typical depression curve. The Gartner curve, for those who don't know it, it usually starts with a new technology hype, and then you go into a kind of aftermath or a hangover, where things are not coming up as brilliantly and they don't scale. So the question about scaling and sustainability of new technology is very critical. The first example I want to give is on smart fields technology in the oil and gas industry. It was the big hype in the 2000 areas, so almost 20 years ago. With the onset of sensors and actuators, all the fields and the assets and facilities could be automatically handled with exception-based human intervention. It didn't happen. It still has some improvements, but not the way it was expected. And the second aspect, which is more to the geosciences here, is also now in subsurface. In machine learning and big data has seen investments from companies like Equinor. 2017, they announced 2 billion Norwegian kroner investment, and to really make digital transformation work across the upstream business, very much on the subsurface side. They have now, not so widely published, that they have halved and slashed that fund because they didn't see the returns on the investment. Yeah, and the remainder of the investment they still continue to do machine learning and digital and all of that, but much less so on the machine learning side and much more so on the data foundation side. So my question to the panel is, What can we do to scale machine learning and big data and geoscience, and how can we make it sustainable, learning from the past?
Thank you. Who would like to answer?
That's a very insightful, great question. Thank you. I think we need to recognize that risk. Sometimes a field is very promising, so people's expectation get ahead of itself. The 2000 internet bubble was real, it popped, but by the end of the day, it was a huge advance compared to what it was before that bubble. And also, you have to. It depends on who you ask. If you ask Geoffrey Hinton whether we're going to see another AI winter, I think his answer is no. We won't see another AI winter because it spreads out so much now. So there is a risk of minor depression, but I don't think that it's going to fall back before what it was like 5 years ago. Yeah. So I wonder what the other panelists think.
Yeah, I think it's a good question, because every method and every new method has to prove that it's worth the issue and worth the money that is spent, and we will see what happens. No one knows. And if it really, so from a business perspective, it's always about, is it worth it? So at the end, and currently I would say it's not only about is it worth it, it's also about marketing. So you simply, sorry Niklas, you simply have to do it to be up, to be hip and modern and on the right track. So if you wouldn't do it, it would be kind of what, that's old-fashioned company there. So we will see what happens in a few years from a business perspective. It's always can always happen that you say, okay, that was nice, we gathered some experiences, but at the end it won't pay out. We will see.
We have another question.
Yeah. Yeah, hello. You already started to discuss about the open data topic. So my question is, a lot of earth science and geoscience is done in public institutions, at least in Germany. And you always or often have the challenge that you cannot access like commercial data, which is often like much better in terms of spatial and spectral resolution. How do you see the perspective in this regard?
Who would like to take that?
So we could give the example of what Norway did some years back to make this national data repository for oil and gas data. So they just sorted out the legislation so that the commercial parties have to deposit their data in this repository after X number of years, depending on the data type. So then it becomes available to the public. You don't have the latest and greatest, but as time goes, it's building up to a huge repository of what was originally commercial data.
Okay. Do we have another question from the audience?
Sorry, just to add to that, we have a similar situation in Quebec where if you do work, you must depose it. One of the major issues is, as was mentioned earlier today, is a lot of it is paper, like scanned PDFs and things that are not, they're digital because they're on a computer, but they're not usable. So machine learning actually is going to participate in making sure that data is digitized properly and made available and usable. So that's another challenge with availability of mining data in particular. Is a lot of it's scans and maps that are not in a real digital format.
Okay, then I would like to ask each and every one of you, we're talking about challenges and opportunities. What do you personally think are the biggest challenges? And Guy, you mentioned areas that will thrive. So I'd like to hear from you, what do you think is the biggest challenge that has to be addressed? And what are the areas where you see any application thriving and where you see the greatest potential?
We didn't talk, but I also think that it is very important. This responsible AI, we call it as responsible AI. This is related to explainable AI, plus also ethical frameworks for responsibly learning from data and algorithms. So this is also very important. So plus physics-based AI.
So you feel the biggest challenge or the problem is that you say one has to look at the responsibility, and where do you see the greatest potential? So what would you say is the...
For example, from the education point of view, we need to educate young minds to develop methods that can respect to data privacy. Mm-hmm. For example, this is very important and challenging, and there are so many things to do here. This was also shortly mentioned yesterday in the panel of yesterday.
Thank you.
One challenge I would like to point to is for the subsurface data is the access to annotated data. So it's under the ground. So it's not that easy. You have the boreholes where you have some. You have the human annotated data and some, but it's on a totally different scale compared to images of objects from daily life. So that's something to work with. And on the opportunity side, we shall, of course, be careful not to overpromise. I think there's over-expectations on many things already with machine learning, things that we are asked that we totally cannot address. But I would like to move into the kind of second tier of analytics. So build that foundation of A to B mappers with the different data. Make sure that the output is of high quality and rich and large and diverse, and feed that into the next level of deep learning algorithms that answer more complex questions. So it's vastly more difficult to do, lots of pitfalls, but I would be super excited to go down that fairway. And then if we succeed, then I think we will deserve to put those letters AI on our slides in the future.
Okay.
Well, from our perspective, or from a company perspective, I would say the challenge is indeed what already was mentioned quite a few times today, is the combination of domain knowledge and data science knowledge. So that is really, I think, a big issue. What can we actually do? What do we need in the company? Where are the pain points? So bring these two things together, that's, I think, quite a difficult task. And the opportunities on the other side, I would say, is what we already said saw in our use case, is really that you can speed up things a lot, and that you can get much more granular information and much more detailed information, which of course is an advantage in our field, doing more exact pricing or enhanced customer satisfaction after an event.
Yes, to go along with the challenge you mentioned, the integration between process-based models and neural networks, I think there's a great challenge, but also a great research opportunity. There are foundational questions regarding what parts of your process-based model are trustworthy, what part are not trustworthy, what can you take in, and to what extent do you take in. So we essentially need a mechanism to rate the different kind of physics you have in your model before you just take them in. So, but how do you exactly do that? I have no answer right now, but I think there are a lot of research opportunities there too.
I would literally like to second everything what has been said, and I'm actually a big fan of our internal training programs, which do not aim towards 2 hours or so. It's really a couple of weeks of training, which every employee can attend, and it really helps to demystify the whole field and give a good impression of what is possible, and also to avoid pitfalls and overestimations by doing that. That's, I think, really important.
For me, the biggest challenge in the mining industry in particular is going to be implementation. So we have two great examples here of companies that invested in AI, have stuff in-house, have owned it, and it's rolled out and it's working and it's adding value. But what I see in the mining industry now is, mining companies doing a contract with IBM or another firm. It's a nice pet project, but it never really gets built into the operations so that the company takes ownership and runs the actual machine learning algorithm and keeps adding value to their project. It's basically a proof of concept, and it works, but I don't know how I'm going to implement it. And that implementation often is very difficult because the people that built it, you own the IP, but you don't own the people that can put it in and make it work. And in terms of the opportunity, I think for me is taking out a lot of the menial tasks. I'll take core logging, for example. If we can have, instead of one of our partners has 24 drill rigs turning, it's basically a factory where 20 geologists are reading core and taking notes and taking very specific small information. It's extremely boring. So if you can have a camera-based scanner system that actually gives you the basic data, and then your job as a geologist is then to challenge the computer and add value and add interpretation, it's a much more pleasant and much more value-added job as a geoscientist to do that rather than reading a box of core.
Thank you.
I had another challenge is the educational system. We have kind of adapted into that, but I have been trying to send my students to computer science classes. It's always major controlled and it's almost always overfill. Like, they can't even get into those classes, and the computer science classes are small. So I think in geosciences, we need geoscientific specific machine learning classes, foundational classes that teach them its basics. We should have examples with data from geosciences field to teach them, as otherwise, I send my students to go take online courses, but none of those examples are like from the geoscientific fields. So that's a challenge. Another challenge is the diversity in the AI research is actually really poor. If you look at the background population in AI, it's way off balance. The especially female to male ratio is poorer than any other industry you've seen. And to that end, you lose that diversity of ideas, lose that diversity of thoughts. So I think that's a challenge. Yeah.
You wanted to add something? No. Okay, thank you.
I agree.
So do we have any more questions from the audience? Yes.
Well, if nobody else is asking,
Go ahead.
I would like to know from the panel what challenges you would like to solve using big data and machine learning in geosciences. So I'm currently seeing we're going through energy transition, we're going through changes and skilling, but I would like to know what kind of business case or societal case or environmental case you would like to solve with machine learning in geosciences.
So, for example, I personally would like to understand really how we can make use of this big amount of data for Earth observation with minimum supervision. So, how we can learn from the data if the labeled data are not sufficient, if the labeled data are not there even. This is a challenge that we are currently considering. So developing machine learning algorithms to learn from huge amount of data for different Earth observation applications, but just with minimum supervision. This is the challenge from my side, from the machine learning point of view.
Thank you. Anyone else want to answer the question?
Sorry to come in again. The question I want to solve is actually totally different from all the things I've talked about. I've always been wondering, can we solve the problem of desalination from a water perspective? Because if you solve the problem of desalination, we could have almost infinite amount of water supply. And right now, we actually have lots of energy coming from solar how do we connect the dots here to make large-scale desalination a possibility? But I have no solution. I have not in that industry, so I'm just throwing that question out there to see if people can help.
Can anyone help? So it seems to remain an open question.
Sorry, for me, one of the problems we can tackle is waste in mining in particular. We do need metals to transition to a green energy, a lot more copper, a lot more aluminum, a lot more nickel and cobalt and so on and so forth. In just the existing operations, I see a terrible amount of waste of good metal being thrown out because we just are not in control of our operations, and the solution to me is geometallurgy. So understanding our deposits better and sequencing the production in a way that maximizes recovery, and also a better planning around how to treat the waste rock and the tailings from these operations. And it's just a matter of understanding and then implementing a sequence and a process that's optimized.
Also had a short chat in one of the breaks with someone who was exploring the seafloor, and we have deposits of valuable minerals on the seafloor. And I think in Norway there's a requirement for the petroleum companies that in order to have activities they need to map the seafloor with all sorts of sensors, including ROVs. And there was another conversation with a gentleman in the geological survey. So geohazard problems can be solved. There's a lot of research out there on predicting avalanches with machine learning and flooding. So there are all sorts of use cases like for the good of society where these things can be applied. And yeah.
Okay. Thank you. Any other questions or comments so far? There at the back. Right there, yeah.
Actually, I like this comment on the examples for geologists or for geophysicists to get closer to machine learning. What can be the examples for geologists or geophysicists, because they are interested in geology and not in machine learning. So it should be something that will enable them to do their job much faster, to get insights in geology much faster and more easy. Then I think there would be motivation. So what can be the examples for geologists?
I absolutely relate to this question. So I'm a geologist myself. Geology is what interests me, learning about the earth. Machine learning is just one of the many tools that I can use to do that. So machine learning is a hot topic now. But as we move along this hype cycle, I think it will still be a key tool in the toolbox. But it will be there amongst many other tools. And it will be there in a form that all geoscientists in this room can exploit this technology. And you don't have to write the code yourself, invent new algorithms or anything. But certainly you should understand in some basic form what is under the hood, what's going on.
So maybe, if I may join in here from the back, I think a good example that plugs into that question would be, I mean, so I'm a geophysicist, but in geology would be you doing image classification. I think that's the major task, and that would be very appealing, I think, to many students to learn, I don't know, TensorFlow using Python on image classification of geological images of, yeah, whatever kind. So I think that would be very appealing to many students.
I think not necessarily the course needs to be about machine learning, but at least data literacy, where people understand the difference between bias and what's good data, what's bad data, and how to get from raw data into predictions. I think there's a huge gap there just in terms of what data looks like, and I think from when I graduated, we didn't talk about data at all. It was all about the rocks and what they look like. And now we're in a world where that's not enough. So to at least transition into a data literacy curriculum, and then that I think naturally flows into machine learning.
Any more questions? Okay, well, talking about questions, it was mentioned before that you have to keep asking questions, and to me it seems a bit like in all areas, so that you need to be open to the learning process. If it's the new generations that are learning, geologists learning about computer science and the other way around, that you can learn from your machine learning processes as well. So it seems like you just have to keep the mind open and learn from each other and keep the learning process going. That would be my main takeaway. And so I would like to say a huge thank you to all of our amazing speakers. Guy de Arne, Eric Larsen, Xiaopeng Chen, Vigim Demir, Niklas Klein, and Thomas Zerbeck. Thank you so much for this great exchange again. Thank you all for your participation. I think there were so many great insights and inspirations and impulses that were set over yesterday and today, and I'm sure that you will have a lot to take with you and to implement into your future work, your projects and your connections. I would like to say a huge thank you to all of our speakers that were here yesterday and today. I would like to, of course, also say a very big thank you to the BMWI for this great location. A thank you to all of you, and to all of you in the live stream as well. And of course, the biggest thank you goes to the BGR for this great organization.